In this lecture, we're going to talk about how you can render Bezier forms in particular, and at the end we'll show you that if you know how to render a Bezier form, you really know how to render any of the other forms we've been talking about. We'll also, in the following lecture, apply these ideas to rendering the teapot, which is the most famous graphics object. I'll give you a small introduction to that in this lecture. So let's start with the idea you want to draw these curves or surfaces that we've talked about, and eventually what you're going to wind up doing is drawing little line segments for the curves, and then for surfaces, eventually getting little quadrilaterals to fill, which you'll convert to pairs of triangles for rendering, because eventually you're going to pass it through the pipeline, and that's what we know how to render. So what it comes down to a large degree is how do you evaluate these polynomials that we've been talking about, that we've derived for all of the different forms, and there are a number of ways of evaluating them. Finite differences is one method we talk about in the book that any of you who've taken numerical analysis may have studied it, but more generally you do some sort of either one of two things. You either do sort of a direct evaluation of the polygons, which is what the old functions that were in the pre-deprecated desktop OpenGLs did. They called them evaluators, but basically what you did was say what's the degree of the polynomial you want to use, and how many times do you want to divide it up before you get all of the little points along it to connect with lines or define your quadrilaterals or triangles. So even though that's been deprecated, as you'll see, it's very easy to recreate that functionality in your own code. But there's actually a far more interesting way that I want to talk about in this lecture, and that's to use this idea of recursive subdivision again and give you what I think is one of the most elegant derivations in computer graphics, and something you can actually apply, and I'll show you that when we talk about the examples in the next lecture. So first thing is, how do you evaluate polynomials? Well, if you want to do and we're going to let's just talk about cubics in these lectures, because everything we say can go on to higher order ones. But as we've been saying, is that cubics are the ones that are used most often in CAD and computer graphics. So one thing you can do is you can say, well, here's this cubic polynomial, and I want to evaluate it for x, y, and z, and maybe w. Well, certainly we're not going to compute u, then u squared, then u cubed. If I just use the parentheses right, I can reduce it to 3 multiplications per evaluation for a given value of u, and that's known as Horner's method, and we can extend that certainly to any other evaluation. Now, if you go a little bit further, and this is in the book, you can say, well, if the points are equidistant apart, the points in u that you're going to use, you can actually completely get rid of multiplications and just use additions by finite differences, which is essentially an approximation to what you do with derivatives, and which becomes exact for equally spaced for a given degree of polynomial. You build up a table and use that table recursively to get the values. But that's not quite as general, and it's probably not done much in computer graphics, so let's not talk about it here. The most interesting method, I think, is called de Castelnau recursion, and there's actually an interesting story behind this. When we talked about Bezier curves, we talked about how Bezier had designed these curves based on Hermite methods when he was designing car shapes in the 50s. It was either Renault or Peugeot. One of them, de Castelnau, worked for one of them, and Bezier worked for the other one. And Bezier's methods became really famous because he was allowed to publish all of these results that he got, and ways of evaluating these nice polynomial curves and surfaces. Well, it turned out that de Castajo was working also in France on exactly the same thing, but he was never allowed to publish. So all of this work, and actually he went much further, especially in terms of how you evaluate these kinds of functions. But he was being never able to publish. All this information was buried in technical reports, and it's probably only like 10, 15 years ago that people discovered that de Castajo had done this stuff earlier and never gotten credit for it. So in the graphics literature now, many people, including Bezier, point this out, that he deserves the recognition. So a lot of people now start calling them de Castajo curves and de Castajo surfaces. So it's an interesting story about being in a place that lets you publish your results or not. But anyhow, his recursion is the basis of the evaluation that we're going to talk about now, and we'll get to this point, this idea that any polynomial is a Bezier polynomial. I'll come back to that point at the end. So the idea is this, that if you take a Bezier curve, so here's a Bezier cubic, it's determined by the 4 points P0, P1, P2, P3. So as we talked about in the last lecture, this curve interpolates the endpoints. It matches this line going between P0 and P1 on the left, and the line between P3 and P2 on the right, and it has to fit inside the convex hull, which we've drawn as this little trapezoid going from P0, P1, P2, P3. Now, suppose I break that somewhere in the middle. So let's assume the middle is where u equals a half. This is u equals 0. This is u equals 1 at this end. So let's break it here at u equals a half, and look at a curve, the part of the curve on the left, and call that L of u, and the one on the right, let's call that R of u. Each of these, now here's the crucial point. Each of these is a Bezier curve if I pick the data correctly. So how could I pick the data? Well, if we just draw it, we could say, well, look, if I know this point here in the center, then I have the point for the right side of L of u and the point for the left side of R of u, and I have the other endpoints from the original curve. So now I need to find 2 points here, L1 and L2, so that I match the slopes at the ends of the left curve, and likewise I have to find R1 and R2 that match the slopes on the right curve. So going backwards then, I say, well, if I have these 4 points for the left curve and the 4 points for the right curve where they share the center point, well, those are the data for a Bezier curve that goes over the range 0 to a half, and I could rescale that to go over 0 to 1. Well, notice what happens. You have this property that says, here's the convex hull applied again, and this convex hull has to be inside of the original convex hull, so it's a closer approximation to the curve. So the idea is, in the end, what I want to do is say, well, look, I'm going to eventually use line segments, and L0, L1, L2, L3 is a much better approximation to the left curve, and then R0, R1, R2, R3 is a good approximation to the right curve. So why don't I draw this line, these connected line segments here, and that's a better approximation than P0, P1, P2, P3. Well, if you don't like that approximation, how can you do better? Well, obviously we use recursion, and we repeat it on the left curve and the right curve until we're close. Well, how can you determine if you're close? Well, if you look at this picture here, well, here's the next one. Let's see, this is essentially the same picture. How do I say if I'm closer? Well, one way is I can always just measure the distance between L1 and the line from L0 to L3, and between L2 and that line, but just dropping a perpendicular here and saying, well, gee, that's close enough. Or I could do something much more simple. I could just take the values of these things at some u, like in the middle, and see if they're close enough. So you can determine when to stop, or you can just do a fixed number of recursive steps. Well, this property where the convex hulls on the left and the right fit inside the original convex hull is known by the name of the variation diminishing property, which is just saying, again, that you get closer and closer and better approximations as you do this subdivision. Now, the problem now is I haven't told you how to get these points. Well, this one you get by just evaluating at u equals a half. How do I get these other values? Well, I won't go through the whole derivation, but it's in the textbook. You can get these, and here's the equation. Let me just give you the equations. The equations turn out to be this because if you use the facts you have, that you have to match the slope, and on the left side, when you match these slopes, you're only going halfway up in u space up because you've changed from going over the whole range 0 to 1, going to half range, so you can get these, and then you can go through the equations and get L1, L2, and R1, R2, and finally get that middle point. Well, here's what these equations come out to be. You get, this is for the left side. You can also get the right side. Here's whether you're taking into account the fact that you're only going over half the range. And once you've done that, here's the final results that you get. They're very elegant, I think. Notice that here's some of the key things here. First, obviously that you can do it. So here's the construction that you see here. So here's the equations you get by just solving what we had on the previous slide, and do the same thing on the right. Notice that there's all 1/2 here. That says, well, gee, I don't really have to do a division. I can do a shift. A division by half is just a shift in the representations, and so all I have to do is shifts and adds here. There's no multiplication involved in this recursion, and that means it's going to be a lot more efficient doing it all shifts and adds. So if you look at these equations differerly, you could say, here's how I get the results. I can compute P1 and P2 over 2 first, then I can compute L1 by just taking P0 plus P1 over 2. I can get this point, then using this point in the center here, P1 plus P2 over 2, I can now divide them in 2 to get L2. I can use the point in the center again, and R2, which is halfway between P2 and P3, divide that in 2, get L2 and R1, divide them in 2, and get the middle point. So you don't actually ever evaluate the original equation to get the value in the middle. You can do that all by this shift and add kind of thing. So I think this is just a great algorithm, and it leads to a pretty efficient way of getting points that are very, very close to the curve and that you use your rendering, and I'll show you the code in the next lecture. So if you get back to this other argument, which just says every curve then is a Bezier curve, well, what do I mean by that? It says, well, if I take a cubic polynomial, if I give you 4 points on it, well, those 4 points are interpolated. So if I go backwards, I could say, given those 4 points, this is an interpolating curve for that particular set of data. But I can apply the same argument and say, well, if I look at that given curve as being a Bezier curve, I can find 4 control points, obviously the 2 interpolating points at the end, and 2 other points that if I apply our definition of a Bezier curve, that particular curve is the Bezier curve for this other set of data. So if I can think about going back and forth between data and say, if I'm given the control points for one type, here's the argument. Suppose I want to render an interpolating curve, and I have the control point data for that interpolating curve. Well, I know it's given as in this form. It's the u's in a little row array times that interpolating matrix times the column of the control point data. But if I can find the control point data for that same curve, which gives us, if I say it's a Bezier curve and it gives me exactly the same curve, then this has to be true, that the same curve is given as the Bezier matrix times this other set of data. Well, if these are the same curves, then MIQ has to be the same as MB times the P data, and that tells me how to get the Bezier data from the control data by just inverting MB and multiplying it times MI. So here's the control point data for that interpolating curve, converting it to looking at it as a Bezier curve. And why do I do that? So I can then go and use that recursive method for Bezier curves in order to give me an interpolating curve. And I can apply the same argument to the Hermite form. I can apply the same argument to the cubic B-splines. And in fact, I have some code on my website from the last edition of the book that does exactly that. There's a nice example if you want to run it there. But basically, you can do this yourself by just figuring out these matrices. And here's one of them here. This is for going from interpolating to Bezier, and here's the one that goes from a cubic B-spline to a Bezier curve, and I use that. Here, I actually have a slide here of that example where I've now. So here's the Bezier curve, taking this data, and then I take the same 4 data points. I say, well, what's the interpolating curve through them? I use my Bezier renderer to do that by converting the data, and here's the same data used as the data for a B-spline, and you get, remember, for the B-splines, we only get a curve that's valid over between the second and third points, so I have to do it again to bring in another data point to get this point, on the left, and another data point to get this part on the right. You also, I think, could see, at least for this case, how this curve sort of bends outward and is not quite as nice and smooth as this Bezier curve that uses the same data. But again, the important point here I wanted to make is that gives me lets me use the same renderer, and certainly this is true for surfaces too. So let's look briefly at surfaces, and since we only have to worry about Bezier, let's just worry about the Bezier surfaces, and let's see what happens to this recursive subdivision to render it. And of course, for the surfaces, you can always use our polynomial evaluations directly to evaluate the B of U and B of V, and then use their product to get the value of any of the blending functions at any value of U and V. But let's look at the subdivision algorithm. So the idea again is that if I go in one direction fixing U, I get a Bezier, Bezier curve in V. If I go in the other direction, I get a Bezier curve in U. And so here's the 16 control points, and here's saying, well, look, why don't I do the recursive subdivision on, so here we're keeping U constant and looking at the curves in V, and here's the 4 curves that I get. I've passed the line through this one, and there's a curve that, well, actually the curve interpolates only the endpoint. So the blacks are the data points. So here's the original data points. I then do a recursive subdivision, and I get, so let's look at the bottom one. I get these 4 points here. Okay, I generate this new black point. Okay, here's the original point. I keep that. Here's the center point. I keep that. I generate these 2 new points over here by my recursive subdivision. I also, if I look at the right half, I generate these 2 new points here, this black one and this white one, and likewise for all of the other curves up here. Now, some of these original points I'm not going to need anymore, and those are the ones I've colored in white. They're no longer going to be needed in order to go on to the next step or use these to render. So the white points are used to derive the left curve and the right curve, but then they're thrown away. So notice for the bottom curve here, these are the 4 points, these black ones, up to the center that determine the left curve, and the 4 points, black points on the right, determine the right curve. Likewise for these other 3 going in this direction. Now I can do exactly the same thing on all of these curves going where V is held constant and U changes. So I can do subdivision on this kind of, notice there's a grayish point. These are gray. These are the original points here. And I can do subdivision on U here, keeping V constant. And the same thing for all the curves determined by the black points holding V constant and varying U. So when you do that, the diagram looks a little complicated, but you get the first subdivision does this. The next subdivision gives you all of these other points here, the black points, and all of these white points have been thrown away in that. But if I look just at this corner and what's left, I have 16 points that are in fact the 16 points that are the control points for this Bezier patch on the left, and likewise the repeated points here plus these other black points to the right here on the bottom right are 16 points for a Bezier patch on this smaller patch, likewise for this upper left and upper right points. So you get 16 points, some repeated, for each of four patches. And the code is a little bit tricky, as we'll see. In order to make it nice and clean, you can do some transposing to switch between U and V. But the basic idea is here is that once we know how to recursively subdivide curves, we know how to recursively subdivide the patches by doing what we did with curves in both the U and the V directions, and we get 4 patches out of that when we keep and the resulting little sub-patch has to be inside the convex hull of its 16 control points, and we keep repeating that until we're satisfied that the control data is close enough to the curve we want or the surface we want, and then we render each of them by dividing. We can do something as simple as when we throw away all the interior points when we're close and just use the 4 corners to determine true 2 triangles, which we render. And in fact, that's what will be in the code that I'll show you in the next lecture. Now, one more remark here is that if you want to get normals, if you're going to do lighting, you need normals to do your lighting calculation. In the old OpenGL, again, deprecated away, was that OpenGL did this automatically, but as you'll see in the next lecture when I show you a couple examples, because these are polynomials, it's easy for us to take these polynomial forms and give analytic forms for the partial derivatives with respect to U and V, and then get an analytic function that we can evaluate for the normals at every point where we evaluate U and V. So that's not very difficult to do, and I'll show you a tiny piece of code that shows you how to add that in, and then that just becomes another vertex attribute. You'll compute a data point by, say, subdivision or direct evaluation for a set of U's and V's, and you can compute the normal by having expressions for these partial derivatives. Likewise, just a reminder again that you can do this for any other curve by converting the data that you have into Bezier data by these matrices that I had earlier in this lecture. Now, what we're going to do in the next lecture is talk about the Utah teapot, which is the data, and you can get the data. I have it on my website for the book. The data's all over the place. It defines 32 Bezier patches. I'll talk about this a little later. Here they are rendered by just drawing lines for constant U and constant V, so it's just polynomial evaluation. I'll show you a couple of ways of rendering it in the next lecture and some of the code that's available on the website. But before leaving this lecture, I wanted to say a couple of things about quadrics. Quadrics, even though we argued at the end of the last lecture that they're a special case of NURBS, we rarely use that because the way quadrics are evaluated is a couple of ways. One is that if you're talking about things like spheres, we can get good approximations by taking lines of constant longitude and constant latitude and get a simple parametric representation. We can do the recursive subdivision of tetrahedra to give us good evaluations for a sphere. And pretty much whatever we do with spheres, we get the other quadrics like ellipsoids and paraboloids and hyperboloids. So generally we have a way of doing that by just really getting a good polygonal approximation. If you look, though, at the quadrics as equations, they all can be written in the following form. We looked at them earlier. We said there's 10 coefficients to determine them. Well, the way that they're determined is that if we look at a little XYZ array, we can write any quadric in the form P transpose AP plus B transpose P plus a constant C. So we've got, this is a 3 by 3, so we've got 9, actually we have 9 coefficients in here, but we can always make this symmetric because all the terms x times z and z times x are the same. So, and we have 3 coefficients here, we have a 4th one here. We only have 6 independent coefficients here, which are the 10 coefficients that we talked about earlier when we just talked about simple representation of quadrics. Well, if you look at this and I put in a ray, this is what happens in ray tracing, is that you say, well, what happens where this intersects a ray? So we can think of that when I render this, I'm going to put a ray through every pixel and see where that ray strikes the object. So into this equation, I'm going to substitute in something of the form P0, where that ray starts, plus alpha times d, where d is the direction that's shooting that ray through a particular pixel, and I have to find what alpha actually intersects that. But look, these are constants in d, they're constants in p. If I stick this equation back up in here into this representation, that's saying, well, gee, it's just a quadratic equation in alpha, and I can use the quadratic formula to exactly give me where the intersections are. Well, what are the possibilities? Well, if there is no real solution, then that says that the ray misses that particular quadric object. If there's 2 solutions, that's giving me the entry and the exit point, where I enter a sphere and where I leave the sphere. And by looking at the distances, I can tell which one I want. And then if there happens to be 1 solution, because those 2, the square root turns out to be 0, then what I get is the ray that's tangent to the quadric, like tangent to the sphere. So this is a particular case where you can render it by other methods, and you know, this works pretty well, and this is pretty much what people do, and is sort of the heart of what we'll talk about when we have a lecture on ray tracing later. But what we want to do now is go on to the next lecture and look at some examples where we're actually rendering that teapot.